Welcome to the Railway BIM workflow using the AEC collection and the Autodesk Construction Cloud. My name is Ben Wardell and I'll be walking through this course with you today. I am a technical marketing manager with Autodesk. I've been with Autodesk for about 4 years. Prior to that, I've worked in the industry, in the civil engineering industry, working as a railway designer and as a roadway designer for about 18 years. I've worked on several different projects from streetcar to light rail transit and even into some high-speed rail projects. So today we're going to go through some of the features, some of the tools that are available for your use, as well as some examples to hopefully give you some ideas of how you can best utilize these tools on your projects that you're working with. As far as the agenda is concerned, we will go over a number of the new features and details and tools that have been added to the platforms to really enhance the rail workflows. And those will look across the AEC collection. We'll then look at some of the specific examples that are available with Dynamo for Civil 3D in rail workflows as well. There are some very unique and very helpful workflows that are available using Dynamo. We'll talk a little bit about IFC 4.3. That is going to act as the connection between Civil 3D corridors and Revit models and how those can be linked together. And then finally, we'll get into digital project delivery, where we'll look at some of these workflows using the AEC collection in combination with each other and how those really help with all the different steps of a project, whether it's in the planning phase, the design phase, into construction, or ultimately operations, and how the Construction Cloud really brings all these things together. So to begin with, we want to look at some of the features that have been added specifically with rail designers in mind and how those features really make the process of designing rail corridors and rail alignments much more efficient. To begin with, Autodesk was really focused on showing this emphasis on rail and rail design. A tab was added in Civil 3D that contained all the different rail tools that were specific to rail alignments. Now in Civil 3D, you've got actual alignments that are rail specific, that contain the different elements that are required in these different types of rail, whether it's high speed or passenger or freight rail. A number of rail assemblies out of the box have been added to Civil 3D as well that are also customized for rail corridors. These are useful when it comes to single track, double track, or multi-track corridors. There's no customization required for these, but you still have the ability to create customizations using Subassembly Composer. Geometry support has been added for multiple different spiral types. This includes spiral types for the majority of high-speed rail corridors, as well as some of the regional or country-specific alignments, such as New South Wales. For existing conditions, LiDAR data acquisition has become much more common, but a lot of users want to know what's the best way to use this data or how can they extract key pieces of information. So these output files that are created in this process, they can be viewed in Recap. Point clouds and point cloud data can actually be linked to InfoWorks, where we can extract key information, in this case, the top of rail lines, from a point cloud, and then we can use those in the Civil 3D file. These same lines can be viewed in section view, and we can actually use those to create a surface from the point cloud that is lightweight but extremely accurate. So then in Civil 3D, we can utilize this data that we created in InfoWorks and from the point cloud, where we can generate the surface from those transverse lines, and the 3D lines that we extracted earlier will act as a basis for the existing rail alignments. We can run a regression analysis to determine the location of the existing rail centerline alignments. And these alignments are fully dynamic and it can be revised as needed. And we could create a profile in this same way since these rail lines are three-dimensional. Another tool that has been added was the platform edge line. Now in this case, we have the ability to specify the location and the length of the platform edge line. All of this information is dynamic and connected to our alignment so that anytime the alignment is adjusted or updated, that platform edge line stays connected and linked to our alignment. We can also adjust and edit the platform edge line itself, and that can be based on rail vehicle criteria as well. We've also added the rail line creation tool. So corridors tend to be chorded in tight curves even if the frequency is tightened. Customers wanted to be able to create rail lines with much tighter tolerances that would actually represent the inside edge or top of rail line. So these lines can be created and edited to meet the exact tolerance required for construction or for reporting. These lines are also dynamically connected to the alignment, so if there's any change in the alignment, the rail lines also update. These rail lines are 3D polylines or can be created as feature lines so that we can create solids from these alignments as well. In this final frame, we can see the difference between those rail lines that are to an exact tolerance and the actual corridor model. Turnouts and crossovers got a big upgrade. So in this tool, we can specify parameters such as the turnout angle, the turnout number, and the direction and side. We can also place the turnouts by certain insertion points, the point of switch, the intersection, the point of frog, and we can control the different display styles by turning those on and off. The turnout is linked to the parent alignment, so we can change the location, the direction, and the side, and it all stays linked to the parent profile. We can add labels of critical points, and we can use the properties dialog to revise the turnout angle. And notice that the labels stay connected to those key points regardless of the angle. In the profile view, we can see the turnout profile that was created, again, based on that parent alignment, and we can connect the turnout to the rest of the profile. Crossovers work in a similar workflow. They're much easier to use, and they can be used if the connecting tracks are parallel or non-parallel. For profile view bands, there have been a number of edits that have been made, particularly when it comes to creating track charts. We can create the cant or super elevation in the chart, and that can be edited dynamically, whether it's the applied cant value or the station location of where that cant is applied. Bands were added to the profile view that represent cant as well as the speed of the rail profile. More recently, we've added the point and alignment proximity band so that we can show station and offset locations to key information such as other alignments within a yard or adjacent to our main alignment, or Kogel points that might represent critical clearance elements or fouling points. Next, we'll get into Dynamo for Civil 3D and some of its specific uses when it comes to rail workflows. This really gives us the ability to add a lot of details to our model that may not otherwise be added. This allows us to create a much more complete and intelligent model. So to start out with, one of the first workflows that we've demonstrated is to place objects along a corridor. In this case, we're placing ties or sleepers that are cant aware, or we could also place rail solids that are represented by feature lines. We can also extract Kogel points using a program like Project Explorer and create a CSV file that represents the location of all of our overhead contact poles. Then we can run the script that will insert those systems elements so that will help us to reduce conflict or rework in the future. We'll show a specific example of that later. And we're not just placing dumb objects along the alignment, we can also place elements with metadata and property set information included. In the CSV file, property details will also be included when those elements are placed. And we can also extract property set data based on the criteria that we set. Specific workflows, such as creating plinths, where we can read the cant information of the corridor for something like direct fixation, and we can control the size, the spacing, and the station limits of the plinths. We can also create a vehicle clearance envelope and make solids to determine any sort of conflicts or fouling points. We can also control the limits and the station locations of where those elements are created. During design and construction, it might be important to be able to see existing conditions or construction progress. In this script, we can actually access photos that were taken in the field and set them up so that they are displayed with a hyperlink within the CAD file. All this data is open standards, and so it can be shared and reused for other projects that have a similar requirement, and it's iterative in nature, meaning once we've updated the alignment and made any adjustments, we can rerun the script and immediately see our results. IFC 4.3 is what makes it possible to connect a Civil 3D corridor to a Revit model. This has been a really popular request for a long time, and this is how it's going to be possible moving forward. In Civil 3D 2022 and later, you now have the ability to run a command called IFC export infra. That's IFC export infra. What this will do is create an IFC file that we can actually go into Revit now and link that file to gain access to all the content that was created in our Civil 3D corridor. And then within the model itself, we can view property set data that was created in Civil 3D. So corridors, Coco points, feature lines, surfaces, and pipe networks, these are all elements that are going to be exported in this process when we create the IFC file. So once we're in Revit, now we have the ability to utilize this property set information. So in this case, we can actually create tags based on those property set details. And here we're labeling the system's elements based on the details that are contained in the Civil 3D file and in the property sets as well. So IFC is an open platform, and it can be viewed in a number of applications. Again, all of them showing this same data that was available and created in Civil 3D. Next, we're going to get into project delivery using the AEC collection in combination with the construction cloud. So at any stage of the project, having data in a common location is really vital. Team members need to have access to whatever the latest design information is, no matter what stage of the project that they're in. So whether they're in the planning and alternatives analysis stage, the design, the build and construction phase, or the operations phase, in all these phases, we need to have access to the data that's associated. And BIM Collaborate Pro is really how all of this is brought together. So we'll take a look at an example project working through the project lifecycle, starting from the planning phase, working through design and into construction, and then ultimately to operations and to handover. We'll take a look at a number of different milestones along that way and focusing on each one of these phases. So in this beginning phase, in the alternatives analysis phase, we have the ability in InfraWorks or in Civil 3D to create these alternatives, and we can look at a number of different concepts in this view. With these alternatives, we can identify a number of critical or key elements, such as restricted areas or environmentally sensitive areas. We can also create multiple alternatives and ultimately come up with a preferred alternative. Within InfraWorks, we can also utilize tools such as traffic movements or pedestrian movements, where we can look at pedestrians moving from one platform to the next. We can even include restrictions in combination with transit schedules. All of this information resides in the construction cloud and can be accessed by anyone on the team that has access or permissions to this data. In the design phase, we're really looking at gathering data and developing this design. So starting with the ArcGIS connector, the team can gather all the data that's available, whether it's property or flood information. And in this case, the survey team will put together the surface details as well as existing information and share it with the rest of the team in the design collaboration module. So the rail discipline now can consume and utilize all those files that were made available by the survey team. And those can be surface files or property files, or in this case, we can even look at some of those point cloud files that were created. Then the detailed geometry and design is done. Again, we talked about some of those tools that are available for creating the alignment, the horizontal and vertical geometry details for the model. Once we have the corridor, then we can move into some other phases such as bridge workflows, where we can connect the corridor from Civil 3D into InfraWorks and use that same InfraWorks bridge in Revit, where some of the structural details are then created and enhanced. And we use the design information that we created in Civil 3D and Revit to create our sheet files. All of this information is then accessed and stored on the construction cloud, whether it's the sheet files, CAD files, or the models. It all lives in this common data environment, so the team has access to these files during design reviews. Designers can comment on the plans during review periods. They can identify issues and then create markups that are all included with these review reports. The next steps are where the designer and the contractors coordinate prior to construction. So here the designer is adding metadata to the model that helps to quantify the materials and the costs. This same data that was available in Civil 3D is also available to view under the properties in the Autodesk viewer. And you can utilize the model coordination module to view all of these disciplines in one aggregated view with the same property set information that was created in Civil 3D and Revit. So let's take a look at an actual real-world situation where model coordination would be very valuable, especially when it comes to this interdisciplinary design coordination. So this is an actual transit project where we ran into this problem, and this is a common coordination issue when dealing with multiple disciplines. We have a set of plan and profile drawings that show a lot of details for construction, but it's really hard with this layout to see if there will be any conflicts or problems prior to construction. There's a lot of symbols, there's a lot of callouts, but it's not very clear if there are any issues. This is a really common delivery style. The systems details aren't much help either. There's a lot of information. We can see the station, the offset, and the dimension details, but we would have no way of knowing that at the end of row 3, this OCS pole was going to be an issue. Even the systems plans aren't going to tell us if there's a problem. We can see a lot of different shading and a lot of symbols, but this won't tell us if there's any kind of problem prior to construction. But we've got a conflict between a pole and some of the special track work. Even when we build the corridor model, we have a lot of information in one place where we can see what's happening, but this can get messy and very busy sometimes. But because we have these tools available to us, and we've walked through some of these rail workflows to create a complete and comprehensive model with these details like the sleepers or the tie locations and the OCS pole locations or the switch machines, we can actually construct a model that is going to tell us if we've got a problem. So once we combine these models together, we get a much better idea of what's going on, and right now we can see where we have that switch machine and that pole that are in conflict with each other. Now, since all the elements are modeled together, now we can see this issue beforehand. So clash detection allows us to compare the model and will tell us when we have a conflict. So a specific item is identified as a clash, and now we can identify this conflict and notify the designer or the contractor prior to construction. So this was an actual example. We'd had a number of field issues to the point where the contractor asked if we could create a model or a simulation that would identify these conflicts prior to construction in order to save time and any kind of rework. This mistake actually cost the design of record about $8,000 that could have been avoided by using these features and this workflow. So during construction, the contractor has access to all this information in the field. So with a tablet in the field, the contractor can look at all of these sheets and all of this information, and in this case, he's looking at a note that was made on the plan sheets that said to verify the condition of some of these existing culverts. He identifies those, he takes pictures and includes those so that they're connected to the drawing and to this RFI. This information is then forwarded to an inspector who reviews the condition of the culvert and determines that the culvert is okay, it just needs to be cleaned out and maintained. Those comments can then be delivered back to the designer of record with this information, again with these pictures and all of this information attached, to identify that this is what needs to be updated. The contractor can also add as-built details in the field. Here he can indicate that a crossover location has to be shifted slightly due to the structural elements of the guideway. This information is updated on the sheets and then relayed back to the designer of record, and this can be updated in the design files to show the new crossover location. All of this information can be used to track these details once the as-built plans are developed and submitted to the owner. So in the final stage of handover, the owner now has access to all these sheets, files, and models that have been created. All the metadata that was added, all these asset cards and detailed information are available in the files that the owner now has possession of, whether they view that in Revit, InfraWorks, or in this case, even GeoBIM. They have access to all the metadata that was used to create and put this model together that really can act as a digital twin of the project that was created. The final result is a high quality and detailed model that is made by linking all the platforms of the AEC collection together intelligently with the Autodesk Construction Cloud. This was the Rail BIM workflow using the AEC collection and the Autodesk Construction Cloud. Thank you for your participation.